0 and GM. So for VG, you got VG equal VDD times R2 divided, so times R2. So this is what represent a voltage divider. So therefore, you take the VDD times R2 divided by the total resistance of R1 and R2. And so that's when you do that, and that and then that calculation would come out to about 5 volt. And then after that, you want to use, so then the next thing you want to do VS, so you use VS equals ID times RS. So you got a 5.5 milliamps times 1.5 kilo ohm. And that should yield about 6.87 volt.
Sam, so you're saying, I guess in this case, you're saying that ID was given?
Yeah, the ID, IDS, ID, so ID is right here, is given.
Oh, I'm sorry.
The one that's high, yeah.
The one that I downloaded, it wasn't given. That's why, or I don't know if it's there and it's, it wasn't obvious to me that it was given.
Yeah, whatever's it's in bold, it's given already. So you don't need to calculate those.
Oh, again, when I downloaded the Excel, it didn't have any values. That's why.
Okay, let me check. What website. Okay, number 12, D lab 20, assignment 20. Okay, so let me check just to make sure. Okay, enable, maximize. Okay, so yeah, so as you can see, line 65.
It's common Prime. Okay, got it. Thank you.
Okay, and then you use this information that's given to solve for all these other ones.
Okay, great. Okay. Thank you.
You're welcome. Okay, stop sharing. Okay, any other question?
The administrative question for Sam from Mr. Pham regarding registration for Tech 2. I'm assuming that I'm going to be successful in completing Tech 1, but do we need a permission code or anything like that?
Not yet.
You will be getting the code as soon as we get those information directly to the from the office from Mid City, and then we'll make announcement here on the Zoom too, so that way everyone would be present to register for class.
Got it. And Sam, what's the last day of class of Tech 1?
According to the schedule, it's for the next incoming for the registration for the summer is June 6th. So June 6th would probably be the last week of the semester for the summer, for the spring.
Got it. Thank you.
Okay. All right. Any other question? Okay, no question.
Okay, so you can go ahead and review last quiz.
Yes, sir. Okay, so we're gonna go over quiz number 7. Quiz number 7. Okay, so for quiz number 7, okay, so quiz number 7. So number 1, to determine the gain of non-inverting amplifier as shown. Okay, so this is non-inverting because the signal is applied to the positive side of the op amp. So the formula is the gain equals 1 plus RF divided by Rin. Okay, so 1 plus RF is the feedback resistance, which is 1.5. And the Rin is the 1.2 kilo ohm. Okay, so if you add that up, so you do that calculation, it comes to about 2.25. So the answer is A as in apple for number 1. For number 2, for the non-inverting amplifier shown, given Vn equals 4.5 volt, determine the current through 1.2 kilo ohm resistor. Okay, so they want to look at this resistance. Current through this resistance. Okay, so I at 1.2 kilo ohms. So you take the Vn divided by the current, divided by the resistance. Okay, so 4.5 volt divided by 1.2 kilo ohm, that will comes up to 3.75 milliamp. So the answer is C as in cat for number 2. 3, for the non-inverting amplifier as shown, given Vin equals 4.5 volt, determine the V out. Okay, so since we know the gain is 2.25, we're going to take the gain, multiply against the Vn, the 4.5 volt, and that should yield about 10.125 volt. So the answer is B as in Bob for number 3. So any question number 1, 2, or 3? Okay, everybody's good. Okay, next step. Okay, so determine the gain, and number 4, determine the gain of the inverting amplifier as shown. Okay, so this is inverting amplifier. Okay, according to this one, because it's applied to the negative side of the op amp. So the gain is AV equals to negative RF divided by RIN. Okay, so so RF is 6.2 kilo ohm, so negative 6.2 kilo ohm divided by 2.2 kilo ohm, that would yield negative 2.8. Okay, so the answer is C as in cat for number 4. 5, for the inverting amplifier shown, given Vn equals 3.5 volt peak to peak, determine the V out. Okay. So since you have the AC signals, so AC signal is going to get inverted, but we just take the gain, which is 2.8 times the voltage input, 3.5. That yield 9.8 volt peak to peak. Okay, the answer is A as an apple for number 5. Okay, for number 6, for the non-inverting amplifier as shown. Okay, so yeah, they're talking about non-inverting, but they're referring to inverting. So so this question is sort of this. Okay, so for the inverting amplifier shown, given Vn equal 3.5 volt peak to peak, determine the current through 6.2 kilo ohm resistor. Okay, so I at 6.2 kilo ohms equal to V out divided by 6.2 kilo ohm. So therefore, you got the V out was 9. This case 9.8 volt divided by 6.2. Okay, so that's how you comes up to 1.59. Okay, so this was supposed to be 9.8 volt peak to peak divided by 6.2 kilo ohm equal to that. Okay. All right, so the answer is A as an apple for number 6. So any question number 4, 5, or 6? Okay, no question, next set. Okay, so this is all about the, okay, in the differential mode, the opposite polarity signal applied to the input. So A as an apple for number 7. This one differential, this one is from the handout, differential input to opposite polarity out of phase signals applied to the input. So the answer is A as an apple for number 7. Now, number 8, the common mode gain. Okay, so common mode gain is very low because it follows this formula. So CMRR equal to the voltage, so the differential voltage divided by the common mode gain. So if you, and then the goal is to get the CMRR to be high. So therefore, in order for this to be very, very high, the ACM had to be very, very low. So the answer is B as in Bob for number 8. Okay. Number 9, for an op amp with negative feedback, the output is, okay, so the negative okay, so the feedback to the inverting amplifier. So the answer is C as in cat for number 9. So this one is what we have right here, the inverting. So you got pretty much the signals goes in, so you got the feedback is coming back this way. Okay, so feedback into the inverting amplifier. Okay, so the answers are number 7, 8, and 9. Okay, so any question on 7, 8, or 9? Okay, no question. Next set. Okay, number 10, a voltage follower has a gain of 1 because what goes in, that's what comes out. So it has a gain of 1. So V out divided by V in, it would be 1. So therefore, the answer is A as an apple for number 10. Now it has no feedback. Resistor is non-inverting. Okay, so it look like let me see, it has all of these. Oh, okay, so 10 look like it. 10 could be D. Okay, I have to check on number 10 here. So right now we'll go just with A, and I need to check on number 10. Okay, I need to check on this one. I'll check later. Okay, I need to put notes on that. Number 10. Okay, number 11, the bandwidth of a DC amplifier have an upper critical frequency of 100 kilohertz is, okay, so the answer is D as in David, which is 0 kilohertz. What it mean that, okay, so the upper critical frequency would be F2, which equal to 100 kilohertz. Therefore, the F1, when it's not stated, another one, now if we said a low pass filter, it would be something different, but this one doesn't state what kind of, which one it is, but it just tells you at the high pass, the upper critical frequency. So therefore, F1 also would be 100 kilohertz. So the bandwidth would be F2 minus F1. Therefore, it's 100 kilohertz. My 100 kilohertz would yield 0 kilohertz. So the answer is D as in David for 11. Number 12, the bandwidth of an AC amplifier having a lower critical frequency of 1 kilohertz and an upper critical frequency of 10 kilohertz is. Okay, so this one is stated. So F1 equals 1 kilohertz and F2, which is the upper, is 10 kilohertz. Therefore, the bandwidth equals to F2 minus F1, or 10 kilohertz minus 1 kilohertz equals to 9 kilohertz. So the answer is B as in Bob for number 12. Okay, any question number 10, 11, or 12? Okay, no question. Next set. Okay, and the value of the, okay, number 13, the value of the current IF in the circuit is, okay, so now this one here is going to be, so we calculate the current through IF, which is right here. Now the current that going through IF, so IF is the same current as going to the input. Okay, so going through RN. So therefore, we're going to say that, okay, now you can calculate the gain, or you can use this one here. So you can say that, so this one, so the voltage wise is going to be the Vn minus the 0, which is the virtual ground, divided by the resistance, which is 2.2, okay? And that should yield about 0.45 milliamps, okay? Or you can calculate the V out for calculate the gain and calculate the V out. That would be also the other way to calculate this, okay? Now, and so the answer is C as in cat for number 13. Number 14, the value of V out in the circuit shown is, okay, so therefore we take the gain, which we calculate in 13 here, which is negative 10. So you got 10 times the 1 volt, 1 volt. Okay, so this is look like we look like most likely going to be a DC input. So therefore, we're going to use the negative 10 gain times the input of 1 volt. That's why we got negative 10 volt output. So it got inverted into here. So 1 volt positive comes out 10 volt, negative 10 volt out coming out. So the answer is B as in Bob for 14. Okay, any question 13 or 14?
Hey, can I see the answers for 4, 5, 6 again?
Okay, let me go ahead and go through it and then go to back in 4, 5, 6. Okay.
Sure, thank you.
All right. Thank you very much. Okay. All right. So look like okay. So that was the end of it. Okay. Now go back to 4, 5, and 6. Okay. 4, 5, and 6.
Thank you.
You're welcome. Okay, any other question? Let me see chat. Okay, there's nothing there. All right. All right, any other question? All right, let me go and stop share. Okay, back to you, Mr. Pham. Thank you.
Thank you, Sam.
You're welcome.
Okay, so the next part today we're talking about the MOSFETs, metal oxide semiconductor FET. So you can see to get a D MOSFET can be operated at up to mode. Okay. They can get either depletion mode or enhancement mode. The enhancement mode sometimes we call depletion enhancement mode FET. Either positive or negative gate voltage can be applied. If you're looking into that symbol for the MOSFET N channel, and that will be P channel. So one arrow coming in and one arrow coming out. Okay. Depletion mode, when negative get to the source, voltage is applied. Enhancement mode, when positive get to the source, voltage is applied. Generally operate in depletion mode. So basically, you can get the MOSFET, okay? They can be working at the depletion mode or enhancement mode, okay? For the depletion MOSFET, they can say either positive or negative gate voltage can be applied. For depletion mode, negative gate to the source applied. However, enhancement mode, when positive gate to the source, voltage is applied. So by looking into the circuitry, you can recognize the MOSFET working on depletion or enhancement. Enhancement mode is MOSFET operate only in the enhancement mode. Okay, N channel require positive gate to the source. P channel require negative gate to the source voltage. Equation stands for characteristic curve differ from that of J FET and D MOSFET. So you know the MOSFET most likely working like what we already done for J However, enhancement is different. Okay. Okay, the MOSFET general transfer characteristic. So if you're looking on the display, then you can see they will be the MOSFET, same thing like JFET we already done. Okay, this is the IDSS and the VGS off. The IDSS VGS equal 0 and at VGS off ID equal 0. One shows display for the N channel and also for the P channel. Okay. Example. For a certain D MOSFET, IDSS 10 milliamp, VGS off minus 8 volt. Is it N channel or P channel? Without looking into the solution, tell me they will be N channel or P channel. Okay, the answer will be N channel. And the question is why you say N channel? I think if VGS off is negative, that's for N channel. VGS off positive, that's P channel. And they want to do calculation ID at VGS equal minus 3 volt. We already know the formula. ID equal IDSS times 1 minus VGS over VGS off square. And that calculation given to you, ID equal 3.91 milliamp. Okay. And number C, calculate ID at VGS equal plus 3 volt. Same thing, using the same formula. And you can calculate to get ID equal 18.9 milliamp. That's a basically very basic in the JFET. The MOSFET, remember, the MOSFET working the same as the JFET, but it's not E, okay? E MOSFET different. Okay, now this one you have to do for me. For a certain the MOSFET IDSS 18 milliamp, VGS off, blood 10 volt. So number A, is this an channel or a P channel? You can tell me the answer quickly.
B
They
channel
will be
B positive.
P channel. The thing is VGS off equal positive. Okay? And then now you're doing calculation for me. At B, what ID equal? Who get the answer for B? Let me know.
6.48 and then 35.28.
You mean on number B, 0.48?
B is 6.48.
6 point.
milliamps.
And C,
It's 35.28 milliamps.
anyone get the same answer?
Looks good.
The thing is, you know, that what I've said, very, very basic. If you can do it, give it to your guy more confident. You don't have to go into too much detail. Okay? Any question on this related problem? Okay. Now, we go to E, MOSFET, transfer characteristic curve. You can see they different from JFET and D, MOSFET. So, at this point in channel, okay, you can see there will be a VGS okay, not VGS up. And that's for the P channel, okay? That is quite different. Now, the equation for the parabolic transfer characteristic curve of a MOSFET differ from that of the JFET and the D MOSFET because the curve stack at VGS rather than VGS up. On the horizontal axis and never intersect the vertical axis. The equation for the MOSFET transfer characteristic curve, this is the formula, ID equal K times VGS minus VGS TS square. The constant K depends on the particular MOSFET and can be determined from the data sheet by taking the specified value of ID. We call ID on, okay, at the given value of VGS. Example, the data sheet, okay, for this MOSFET give ID on 500 milliamp at VGS equal 10 volt and VGS TS equal 1 volt. They want to know the drain current for VGS equal 5 volt. So, in order to calculate the ID, okay, and you know they equal K times VGS minus VGS TS square. And the first thing you have to do, calculate K. K equal ID on, okay, divide VGS minus VGS TH squared. There will be a 500 milliamp. VGS is 10 volt. That's what they given you right here. Minus 1 volt. Okay, that VGS TH squared given to you 6.17 milliamp per voltage square. So you see that the way calculation for a MOSFET quite different. Okay, and now next, using the K value, we calculate the ID for GS VGS equal 5 volt. ID equal K times VGS minus VGS TH squared. And that given to you. I believe 98.7 milliamp. We already go to that example. And now you do for me related problem. The data sheet MOSFET given ID on 100 milliamp at VGS equal 8 volt and VGS TH equal 4 volt. Find ID when VGS equal 6 volt. So go ahead and do for me. First thing you need to calculate the K. Okay. The K we get ID on. Divide VGS minus VGS TH. Square. Okay, go ahead and calculate telling me what you get.
Uh, 6.25.
55. Is it correct?
6.25.
6.25. What the unit? Milliamp
Correct, milliamp.
per V square. And then you can calculate the ID. I believe there will be a K time. Okay. VGS minus VGS TH. Square.
Uh, 25 milliamps.
25 milliamp. Okay, if you get a different answer, let me know. Okay, if it's not, let's see what else. Handling precaution. On most devices are subject to damage from electrostatic discharge, ESD. That's why when you get hiring for a company, first you will be get trending for ESD. Okay. Most device should be shipped and stored in conductive form. All instrument and a metal bench used in assembly or test should be connected to the arc route. The assemblers or handlers which should be connected to the arc route with the length of wire and a high value series resistor. Never remove and MOSFET device from the circuit while power is on. Do not apply signal while DC power is off. This is very, very basically, you must know when you get the offer job, first thing they will be training for you. Okay? To make sure you know how to handle the MOSFET device. Okay, see what example here. Determine the drain to the source voltage in the circuit shown. The MOSFET data sheet given VGS off equal -8 volt and IDSS equal 12 milliamp. Okay. Solution. Since VGS equal 0, then ID equal IDSS equal 12 milliamp. You understand on that? VGS equal 0. So basically you understand it, you get a positive VGS. Both sides is rounded. Okay. VGS with the source connected to the route. So that's why you're able to get the ID at and equal to ID. Then you can calculate the VDS. That means the voltage from the drain to the source equal VDD minus IDSS times RD. That given you 10.6 volt. Any confusion, anything, do not can follow it. Just bring up the question. Okay. Now, example. Determine VGS and VDS for E MOSFET. This will be an E MOSFET. Circuit shown. Assume this particular MOSFET has a minimum value of ID on 200 milliamp at VGS equal 4 volt and VGS TS equal 2 volt. So the first thing you need to calculate the VGS. That means you can see VG right here. That will be a add. Using the voltage divider. That means you take the VDD times R2, divide to R1 plus R2. That given you 3.13 volt. To determine VDS, first you need to do calculation for the K, okay? Like we already did it. Okay, K equal IDR. Divide VGS minus VGS TS square. That given you 50 milliamp per voltage square. And now you want to calculate the VDS. VDS equal VDD minus ID time RD. That given you 11.2 volt. Now you can see a little better how to deal with the MOSFET. Any question? Okay, so basically that will be summarized. Okay, and they given to you anything we need. We already talking about JFET. Okay, and just try to give you summarize all of the basic formula. Okay, like for the gate source junction must be reverse bias VGS control current ID value of VDS at which ID become constant is the pin of voltage. Okay, value of VGS at which ID becomes 0 is the cutoff voltage. IDSS is the drain current when VGS equal 0. That at the beginning, we already go through it, okay? That is the maximum current, okay? At VGS shorted of VGS equal 0. And they give you the formula, how to calculate the ID, how to calculate the GM and GM 0. And the MOSFET, except that it can be operated in enhancement mode. The MOSFET characteristics are the same as the JFET. Okay, the depletion mode, N channel VGS negative, and P channel VGS positive. If you're using enhancement mode, N channel VGS positive, P channel VGS negative. VGS control ID. The value of VGS at which ID becomes 0 is the cutoff voltage. Okay. IDSS is the drain current when VGS equals 0. And transfer characteristic ID equal same thing. Okay. That's a very good summary. When you're reading through it, you understand everything. That'd be good. A MOSFET. There are no depletion mode and characteristic differ from the MOSFET. Enhancement mode N channel VGS positive, P channel VGS negative, VGS control ID. Value of VGS at which ID begin in the threshold voltage VGS TH. Then for characteristic ID equal K time VGS minus VGS TH square. And also you have to know the formula, how to calculate the K value. Okay, K in formula can be calculated by submitting data sheet value. So basically, most of the data here will be in the data sheet for the E MOSFET. Okay, you get any question, anything? Okay, E MOSFET bias. You can using voltage divider bias or drain feedback bias. Okay. If you're looking into the circuitry, recognize which one. Let's see, example. The VGS and the VDS for the E MOSFET circuit. So assume this particular MOSFET has a minimum value of IDR 100 milliamp and VGS on 6 volt and VGS TH equal 4 volt. So now they want you to do that calculation. Go ahead and do 1, 2, 3, and 4. If you can do it without looking into the formula, you're really good. Go ahead and do it for me. I want the answer. You can see on that they're not using the graphic. Okay, who get the VGS?
18.2 volts.
How many volt?
18.2.
Can you say again?
18. 18.2.
1.8.
18. 18.2.
18.2. Is it right?
I get 1.8 volt.
Okay. The other one get 1.8.
100.
Try to understand. This is a very, very basic. You can get quickly. And who get the K? What K equal?
$20.6.
What?
20.6.
Okay, let's see, just a minute. Milliamp per V square. And I want ID. If you get an answer different, let me know.
Actually, I get 25 milliamp per V square.
Okay, how come to get a different? Is it same? You get any answer?
Come up to K is 25 milliamps V square.
Yeah, it's 100 divided by 20, right? By 25.
Correct.
ID.
So 100 milliamps?
What ID equal?
100 milliamps?
How many? Can you repeat for me?
Yeah, it's 100 milliamps.
100 milliamp.
Huh?
You say 100 milliamp?
Yes, 100 milliamps.
I get 121 milliamp.
How come quite different? Let's say ID. Okay, VGS minus VGS TH. Is it K equal 25, right?
Yeah, so it's 25, and then if you take that VGS minus VGS TH, then that's 4. That's
So what ID you get?
100 milliamp.
You forgot to square it.
No, because it's 6 minus 4, it's 2. 2 times 2 is 4. 4 times 25 is 100.
Let's see, it should be 1.8 minus 4. No, that's wrong.
So basically, that one you can take at 25 time VGS mean VG 1.8.
Oh, you're right. I'm wrong.
Okay. Minus 4. So you get answer will be what? ID.
It is 121.
How come I get 12.1?
Yeah, BDS 12.1.
Is it 12.1?
Yes, BDS. No, sir, the BDS is the ID is 121. BDS is 12.1.
VGS.
That's the next question. So for this one is 121 milliamp, Mr. Pham.
Oh, you get ID 121?
121 milliamp.
Okay, now what I did wrong in here?
You didn't do anything wrong. 1.8 minus 4 is equal to 2 point something. Then you square it. Then that becomes 4 something times 25 is equal to 121.
Okay, let I try again on my calculator. 1.8 minus 4 square.
You should get 4.84.
4.84 times 25.
Right, 121.
121. Correct. Thank you. And VDF.
That's the 12.1, sir.
VDF will be equal to VDD. ID time RD. Should be 20 minus 121 times 100 ohm. Let's see. 20 ID 121 time 0.1. You have to change it to the kilo. The thing that you're using milliamp. I get around 7.9.
Agree.
Okay, so any question in this example? Number 1, 2, 3, and 4.
I got a question about number 4.
Okay, go ahead.
Would VS equal ID times RD? With this, with a JFET or
Yeah.
MOSFET?
That means you take a different voltage between 20 volt VDD and voltage drop across RD. That's what you get the VDS.
Right.
Remember, D right here. Add in here. That means this voltage here.
Okay.
Only thing you pay attention on when you multiply 121 milliamp to the resistor, then you have to change the resistor to kilo ohm. So they cancel. For kilo and milli, okay? One will be minus 10 power minus 3. One will be time of 3. Okay, any question on that problem? Let's see what's going on here. Still E MOSFET. Determine the amount of the drain current in the circuit cell. They get a meter, they give it to you the value of VGF 8.5 volt. The MOSFET had VGF equal 3 volt. Have seen this is the drain feedback configuration. they're telling you VDS equal VGS. This is the D here. S here. VGS. So they want to calculate the ID. It look like a simple problem, a little tricky on that problem. You know, you want to calculate the ID. VDD minus VDS divide RD. Okay. Okay, see what you get.
That's 2.5 milliamp.
Just a minute. I get 1.38.
Yeah, you know what? I misrepresented where you labeled source with 5 for some reason and I subtracted, but yeah, you're right.
Make sure you have to pay attention much on 3 things. Bipolar transistor, operation amplifier, JFET, and also including the filter. That's what normally you will be working on. Or interview, they will be asking. Oh, this is the review. Should a P channel JFET have a positive or negative VGF? Now you can answer right away, right? P channel JFET, you get the positive VGF. In a certain cell bias and channel JFET circuit, ID equal 8 milliamp and R at 1 kilo ohm. They want VGF. So you know number 2. Okay, on this formula, what VG? What we add? You understand in the cell bias, VGS will be equal. Correct? And VS will be equal ID time RF. The thing is in the JFET, ID on the time will be the same as the IS. So VS equal IS times IS, but you get the same thing, ID times IS. Okay, so what I like you guys to do, try to go to number 3, 4, 5, and also number 1, 2, and 3. That's a very good review. Okay, try to see you can do it. And the next meeting, we'll be talking about that. Got that? No more. Okay. So now I will stop that lecture and Sam will be given to you the quiz number 8. Okay, let I stop that one.
Okay, sounds good. Let me see. Let me go set this up real quick. Slideshow. Transition. Transition everything. Just check, make sure everything is correct. Okay, I'm ready. Okay, so make sure you download the answer sheet from the website. And here we go. Okay, share screen. Okay, slideshow. Start from current. Okay, so that's pretty much it. And so make sure you upload on the answer sheet up to the website before 12 noon tomorrow. And that's pretty much it.
Sam, there was only 18 questions, right? As though the answer sheet, I think it was 20.
Correct. There's only 18 questions.
Hi, thank you.
Okay, you're welcome. Okay. Anything else? Anybody have any question, any comment before we call it in for the night?
Thank you, Sam. Thank you, Mr. Pham. Great class.
Okay, thank you, Jose.
Okay, so good night, everyone.
Good night.
Thank you, Mr. Pham. Good night.
Good night.